Yeah, hi everyone. I can see that there are about five of you there. Uh, just a quick thing. All those who are actually watching, can you please comment in the section so that I at least know and I'm aware. Also, whatever topic you feel that you want me to revise today, apart from the two things that we are already doing, which is thermodynamics and chemical equilibrium, you can please comment in the post. So there are two comments that are there on the YouTube. One is a public comment, and second is a live chat. You can use any of those. That should not be a problem. So just post, who all are present. If you can just post your names, or you can just post uh, and name, and if there is any topic or any question that you have, any query you have, you can also post that so that I can, in the subsequent uh, session, I can actually, I mean, as I go through the topics, I can actually deal with them accordingly. So I'm also going to post the same in the group. Uh, yeah, yes, the class has started. There are a few queries where people want to know that whether the class has started or not. Okay, good. Okay, so yes, let me check if you have any queries as such. Oh, fantastic. So Sachi is here, Mansi is here, Shaumik is here, Arpita is there, Ananya. Uh, Sir, can you revise organic chemistry? Okay, good. I'll do that, Sachi. Uh, okay, Ronak is there. Fantastic. So I think there are a few guys, and there is a request for organic chemistry. And I think Aditya also wanted me to do, but he's incidentally not there on the on the uh, call or this class today. So maybe he wanted me to do with thermodynamics. Okay, Aditya is also there. Fantastic. Aditya, you wanted thermochemistry, is it? Yeah, all anyone who wants any topic to be revised, we have next 2 hours, and the good part of an online session is that this will be recorded for one, so you can always go back and revise it. The second thing is that I have enough bandwidth to actually take in topics which we all can do together. So there is no hurry as happens in the physical class. So we can deal with all these topics one by one, and you would also be comfortable having them together. Okay. So just please post on any comments. Sachi is saying organic chemistry. So I'm going to start with organic chemistry because that's what she wants. Um, yeah. So give me 1 minute. I'm just sharing my screen with you guys. Yeah, there it is now. Yeah, in a moment, I think you should be able to see my screen because I have just shared that. Uh, yes. So I think you guys should be able to see the screen now. If you don't have any screen, there are two ways that you can quickly reach out to me, because by the time you reach out to me, maybe I go to the next, I have gone a bit ahead. So feel free to immediately reach out. One is, of course, you can put up a WhatsApp message. So I also have my, WhatsApp with me. Or second, you can just comment in the YouTube section. So from time and again, every 5-10 minutes, I'll be checking the YouTube section so that I am aware that you guys are there. Okay, Aishwarya is also there. That's good. That's nice. I think, yeah. So there are more than enough people now. Let's begin. So this is for organic chemistry because you guys had a query on that. Okay. So 1 second. Right. So I think most of you do not have a problem in identifying the compound. So the first thing in organic chemistry is basically classification. Okay. So where we are actually able to deal with what are the different types of compounds that we have. Where majorly there are saturated and unsaturated. We also have benzene-like compounds, but thankfully you don't have much of equations on them. So basically, we have saturated and we have unsaturated. Saturated means something that cannot be added. All those compounds where anything cannot be added any further. The name itself says that it is saturated. Now, saturated compounds definitely mean alkane, whereas unsaturated means your alkene and alkynes. So in alkene and alkynes, you basically have a bond which is at least one bond which is a double or triple bond, and therefore there are much more. additions that you can do. Mostly hydrogen is added, but apart from hydrogen, you can also keep on adding other compounds like chlorine, HBr. So all of those compounds can be added. So that's saturated and unsaturated. The first thing that you need to know in organic chemistry is the classification. Uh, Give me 1 second. I'm also right now. Actually the things that you guys really get confused about, I'm going to touch base. I'm going to touch base on those first. So now I think by this time everyone is aware of. Let me quickly check if anyone else has come in. Okay, these are the ones. Okay, fine. Now there are 13 of you. Perfect. So now there are two major points that people generally are confused about. One is the nomenclature, and second thing that you guys are generally confused about is the reactions. What are the different reactions? How to really think about it, etc. So I'm going to give you an overview of all of these, and I'm also going to share some tricks and tips with you so that you are able to really gauge. Sometimes it's very difficult to remember everything. That's a common doubt that most of you have asked. Sir, how do we really remember all of these equations? And is there a way that we can, kind of have some thumb rules through which we can actually be able to decipher what we want to achieve in the reaction? So yes, there are thumb rules as well. So let's look at nomenclatures to begin with. So these are the three things that we will see in organic chemistry. So let's keep this first maybe half an hour for organic chem, and then we can go to thermochemistry and chemical equilibrium. So let's look at nomenclature. I'm quickly going to revise the rules. I don't think so that anyone would ask you the rules of nomenclature per se, as in saying that write down the rules, but they will definitely ask you to name compounds or identify the compound or the compound structure with the help of a given name. The first rule is longest chain. Longest chain. Now, I'm going to also tell you that you guys should be aware about two things now, because earlier, we were not able to do because we were not exposed to functional groups and all. So remember that functional group functional group, which is basically, if people are forgotten, functional group is any group that defines the chemical properties. For example, OH, chlorine is also considered as a functional group, although it is not considered in nomenclature. I will tell this exception separately. Like OH, then you have C double bond O, then you have COOH. So all these are functional groups, and there are two more parts of the molecule which are also important, although they are not specifically called as compounds, functional groups, which are the double bond and the triple bond. Okay, so the double bond and triple bond, I will write this if you don't understand. This is the double bond, and this is the carbon carbon triple bond. Okay, these two, although are not directly technically functional groups, they are important in nomenclature. So let's understand the first rule. Choose the longest chain. That's the first rule, longest chain. Now, if you have a functional group except chlorine, so I'm going to mark this with a pink, except chlorine, or for that matter, halogens. Except for chlorine and halogens, if you have any functional group, the longest chain should invariably have the functional group with it. So must have functional groups. Okay. So it has to be longest chain, but only that chain which has functional group. You will always realize that when you have a functional group, begin with the functional group from that end. I'm going to give you an example. You have carbon, 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 carbon here. Okay, this. Now, incidentally, everyone would think that, okay, if this was the compound given to me, I would rather take this as my longest chain. But if there is a chlorine here, if there is a chlorine here, sorry, an alcohol. I told you that chlorines generally are not really considered as functional groups, but if there is an alcohol, then in spite of this being the carbon-carbon longest chain, which has 6 carbons, this is treated as the longest chain. So this is correct and this is wrong. I'm writing it here. Why this is treated as the longest chain is because with the functional group imbibed in it, this is the longest chain that is possible. Okay, so I have two options here. This is 1 2 3 4. I could have gone straight, or I could have come down, which is 1 2 3 4 5. I have 5 carbons here. There is a chain which has 6 carbons. Please note, there is a chain which has 6 carbons. That is a wrong selection. Why? Because it does not contain the functional group. So longest chain with functional group is the first rule. If there is an alkene or alkyne in the compound, then the longest chain should have alkyne and alkane as well. So I'm going to write this as functional group plus unsaturated bonds. which simply means that the double or triple bond, unsaturated bonds. There are a lot of possibilities that you guys can generally think about. You might say, sir, what happens if there is a functional group and double bond? What happens if there are 2 or 3 double bonds? In all of those, there is a single rule that you should remember: use maximum functional groups plus bonds plus longest chain. Okay, so wherever, in whichever chain you will find maximum functional groups or maximum functional group plus bond, so I'm going to make here a bracket. Sometimes you might find that there are 3 functional groups, sometimes you might find that there are 2 functional groups and 1 bond. Both of them are considered equal. Having said this, there is a priority list of functional bonds which I have given to you. The priority list, if you still don't have, I'm going to just flash this here in the screen, because it will be there in the YouTube, and you can always anytime go back and check this list. So if you want to have the priority list of nomenclature, I'm going to show you that. Carbon compound. Yeah. So you guys can also Google out. There's no difficulty in it. But just instead of writing it here, I'm going to write it, show it here. So here it is clearly mentioned carboxylic acid. If there is a fight between carboxylic acid and alcohol, choose carboxylic acid. If there is a fight between ester and nitrile, choose ester. So on and so forth. Now a few of these functional groups are not there for you. This is clearly there on the YouTube. Just feel free to go to YouTube, swipe here whenever you are in doubt, pause, learn this, and then you can come back. There is an acronym that will also be possible. You can just Google out. There is a acronym which I'm not going to say here because for various reasons. But you can just have an acronym memorized, and that acronym will give you a priority of the order. You, like we have the acronym for chemical reactivity, metal reactivity. Similarly, there is also an acronym for this. Okay, let's go back to our rules. Let me quickly check if everything is good on the YouTube. Okay, Tripan, Neha, and Kirtana has also joined. Good, welcome, guys. The first minutes of this video has been lost because I was silent. So I will try and trim that after this. But you can just follow from wherever you have. Okay, let me quickly check if if everything is fine. Everyone, are you able to see me? Can you quickly just confirm that if you're able to see my screen? Because I'm not sure if the screen is visible. I have not been able to see the screen anywhere here. So can you please confirm if you are able to see my screen on the YouTube? Yeah, I think you are able to see. There's not no problem. Okay, good. So yeah, so things are fine. Okay. Okay, I think it's going good. I'm gonna pull this up. Okay, Tripan is saying okay, it's visible. So that's good. Thanks, Tripan. Excellent. So let's go to the next rule. So the first rule is clear: longest chain with maximum functional group plus bonds. And if you have a fight in functional groups, also refer to the list that I have just mentioned. That's the first thing. Okay. Second. Now let's go to the second rule. The second rule says that the numbering should have the lowest sum. Okay, the numbering should have lowest sum. Now this lowest sum is basically this also is diluted a bit whenever you have functional group. So if you have a functional group, simply start numbering from the carbon which has the functional group. Without functional group, if you have a carbon, then you consider about numbering lowest sum. Now what numbering am I talking about? I am talking about numbering of the branches. I'm going to quickly show you one more example. Let's say this is the one, this is the one. Okay, and here. Okay, there is one here, a carbon, 2 carbons here. Now this is a chain. Now the longest chain is typically this. Okay, this is the longest chain, the one that I'm drawing with the pink color. That's the longest chain. Now it's very easy to identify the longest chain. In fact, if you really see, this also is a longest chain, and there is no problem with that. Okay, whether I take this or I take this, the compound's name will not be different. This is a test for you to identify symmetries. Listen to this carefully. This is a test for you to identify symmetries. Whenever compounds through two or more different structures will have the same name, it is okay to use that name. But even if you can find one structure which you have chosen in this longest chain where you will get a different name, you are in a problem and you have to check again. For example, I have chosen this chain, or I have chosen straight chain. Let me name them A and B and C and B. Whether I check whether I choose A B or whether I choose C B, in both of these scenarios, the name of my compound is not going to change because there is a symmetry, absolute symmetry. Therefore, it is okay to choose any name. If the name changes, then I have to think about all the other rules. That's point number one. Let me, just for your slight complexity, let me choose CB as the chain. The moment I choose CB as the chain, whatever I am drawing in blue are the branches. So look at this like a tree. So this is the bark of the tree, and these are its branches. So there is a branch here, there is a branch here, and there is a branch here. Whereas this is the bark, the bark or the trunk, the trunk of the tree. So the one that I've shaded with a lot of blue thing is the trunk, and these three are its branches. Now whenever you have branches, you number the branches. Okay, you number from both the ends. For example, you can number from here, let's call it as n1, or you can number here, which let's call it as n2. Let me number it from B, or we can call it as B as well, B and uh, A. So B and C, sorry, in our case. So this is our B and this is our C. Let's try and number them. This is 1, 2, 3, 4, 5, 6, 7. If I number this way, my branches are, so I'm going to write here as BC, the orientation of BC bar, like a vector. Like a vector, I'm saying BC bar, my numbering of branches comes out to be 3, 4, and 5. If I take CB bar, Sorry for a small interruption in between. Let me quickly check if everything is okay. Okay. Yeah. Yeah, sorry guys, I lost a bit, in between. I got lost a bit in between, so there was a disconnection here because of some power issues. So I'm back. Yeah, so I was saying that we have two ways, B and C. So from one side we can go as 1, 2, 3, 4, 5, 6, 7, and I get BC bar as 3, 4, 5, whereas CB bar, if I really do, I get the connection, the numbers as 3, 4, and 5 as well. Okay, so if I go from CB bar, here are the numbers. Let me draw it with a different color. So from C, this is 1, this is 2, this is 3, 4, 5, 6, and 7. So this is interesting. You see, on both the sides, I'm actually getting as 3, 4, and 5. Now, in this scenario, had I had a case where I would have got 2, 3, 4, then uh, yeah, guys, can someone quickly confirm if you are able to see me? And if everything is fine for everyone, if you guys are there, anyone can just quickly put a yes, like last time people did. Okay, right. Yes, okay, perfect. Aishwarya is saying yes, so it seems things are okay. So great. So in CB bar, it's 3, 4, 5. Now in this scenario, the numbering from either side, in the sense of lowest number, does not matter because both of them are correct. Now, how would I go about this? Here, if there is a clash in number, the next rule will follow, which is the alphabetical order. Okay, in alphabetical order, I know that this group. Check this. I am writing this in another color again. This group is a methyl group. Okay, this group is an ethyl group, and this group is also an ethyl group. And since there are two ethyls, and ethyl is alphabetically senior to methyl because of E instead of M, I would choose the numbering from this side. Okay, so CB bar is more correct in this sense, because the next rule will follow. And the next rule here, so a quick recap: where were we? Longest chain was the first rule, numbering of lowest sum is the second rule. Here the lowest sum incidentally were both the same, so we end up going to the third rule. And the third rule says that you always have to write the substituents. Substituents are the branches. Please remember, I had shown you what the branches are. You have to write the substituents in alphabetical order. Okay, now please note guys, you pay attention to this. This is very important. Both of them are ethyl, so this compound is written as 3,4 diethyl. In this 3,4 diethyl, di D does not count. Ethyl counts, E counts. This is what counts. And then we write this as 5 methyl or methyl. Okay, so it is the E and D, E and M that count. So the group name counts. The di, tri, tetra does not count. Also, please note that the numbers are written and then all the groups are written together. It is not written as 3 ethyl and then again 4 ethyl. No, it is written as 3, 4 diethyl. Why I'm writing diethyl? Because there are two ethylene ethyl groups. So there could be ethyl, methyl, propyl, butyl, and all of those, right? So this is a very important rule. And then the third rule follows is write the substituents in alphabetical order after the before the root. Okay, before the root. What is the root? The root is the longest chain that we are mentioned. So this is, in this scenario, this is 3, 4 dimethyl, 5 ethyl. Since there are 7, it is an heptane. Heptane. Now there is a very important point. Had this compound had an alcohol here, I'm just showing a variation, so therefore I'm going to show with another color. Now let's say the compound had at this carbon an alcohol. I would have chosen this chain from here. I would have started from here, irrespective of whatever else was there. If I would have started from here, I would have chosen, I have two paths now, 1, 2, 3 here, and here also 1, 2, 3. Now in these two paths, where are the larger substituents? So I find on this path there is one substituent, on this path also there is one substituent. Okay, now that is also same. Now because there are one substituents and the chain length both are the same, I will again go to the alphabetical order and I will say, okay, here there is an ethyl. So the correct order would be from this carbon to ending at this carbon. Okay. If you did not understand this, please go back to the YouTube channel, pause slowly, listen, hear me out, and then try and make a sense. If you have any doubts, please feel free to actually put in your doubts in the comment in the section, and I'll be happy to address them. So now we have seen the nomenclature, in a short. The only difference that comes with functional groups is there is an additional rule. In the functional group, we always consider the root. We always consider as the root as a derivative of the functional group, and therefore if it is an alcohol, which is the OH group, we would say that this is an, let's say for example, an heptanol. Okay, the previous compound would have been an heptanol. Now in that also, please note, it is not always that the OH will be at the end carbon. So you generally write hept, that's whatever number it is, 2, 3, 4, wherever it is, write that number, say 2 nol hepta, sorry, heptan to all. Okay, so it is just the ol that comes at the end, heptan to all. Okay, there is a hyphen that you can use as a separator between the words and the numbers. Please note, hyphen is used only between words and numbers. Generally between words and words, or between numbers and numbers, definitely use a comma. Between words and words, there is no need to use anything. Between numbers and words, you can use a hyphen. So I have given you these rules very clearly and very distinctly, although in the class we have mentioned the same, but because of too many doubts that come in, maybe you guys might not have really got a sense of it. But now here you can always rewind and check these rules and listen to them again and again. Okay, so that's a quick revision on nomenclature. I think all you guys, rest of the things, carboxylic acids, we call this as oic acids. Then whenever we have a ketone, we call that as for example, an heptone or a pentone, so we end it with an one. Similarly, whenever you're an aldehyde, we call it an al. So al, that's how you end it. For example, heptanal, that's how you end it. So you have all of these with you, and now let's go to the next point. If you have any doubts, please feel free to share. Sir saying that, for example, you want a specific nomenclature of a compound. You can also send me a pic. You can send me comment on that. Any which ways, whichever you're comfortable. Just get your doubts clear right now. Okay, so now from here, let's go to the to our reactions. Now, please note that for any functional group, there are three things that have been mentioned in your textbook. First is the properties. Second is actually reactions, and third is generally uses. Okay, in the reactions there are two parts. One is the preparatory reactions or preparations. Second is simple reactions, means after the molecule, where does it go. I'm going to touch upon a few very basic and very important reactions. The first reaction that I'm going to talk to you about, and these are in no particular order, these are just taken out of the entire lot of reactions that you have, but the reactions that you cannot miss out on. If this reactions you miss out on, then you are in trouble. Okay, so I'm going to talk about all of those reactions that are extremely important for you. The first reaction that is important for you is from alkene to alcohol. Anytime you have a C double bond C, okay, you end up doing a hydrolysis. Okay, so you end up doing a hydrolysis with H2SO4 and water. Okay, uh, H2O. Okay, so this is a dilute H2SO4. Now people keep on asking me, dilute, concentrated, sir, this is a temperature, that is a temperature. I think your teachers would like to have you the temperatures that are there in your textbooks, but if you really look at the JE, the larger exams, they are not very particular about the temperatures, except that you need to have the sense whether it is cold or hot. You cannot say that, okay, something was at 400 degree Kelvin, and then you directly say that, okay, no, dilute H2SO for at room temperature. That will be wrong. But you can simply say this as delta. Delta means something that is hot or not. Okay, so so alkene with H2SO4, initially it actually ends up giving you carbon plus HSO4. Okay, and this further, if you hydrolyze, so the double bond, your HSO4, this is how the carbon breaks, and this hydrogen goes here, this molecule gets here, and when you actually go further and hydrolyze it, you end up getting an alcohol. Okay, so you end up getting a CH and a COH. So this is one reaction that you should not really miss out on. The second reaction that you should not really miss out on is from alkyl halides. So when you have a carbon which has a chlorine in it, or any alkene in it, for example, any alkyl halide in it, for example, halogen, like chlorine, bromine, iodine, all of that. In any of this situation, whenever you use aqueous KOH, whenever you use aqueous KOH, you will end up getting an alcohol. So nothing, it's just a substitution reaction. The chlorine here goes out and the OH minus from the aqueous KOH gets in. So you simply end up getting an alcohol here. I hope you understand the way that I'm writing. I'm not writing the entire compound. I'm just showing you the action points where the real action of the reaction happens. So this is a simple reaction of substitution. Remember that with aqueous, the important point here is aqueous KOH. I'm repeating this again and again. This aqueous part is important. Instead of aqueous, if you use alcoholic, you'll end up getting an alkene. So I will write this here itself. So you end up using alcoholic KOH. Okay, uh, you'll end up getting a alkene. Okay, okay. So you end up, yeah, that's one. Now. Okay, so that's one. Now, industrially, alcohols are prepared in a lot of different ways. The one of the most important ways that industrial alcohols are prepared is alkenes. That's by direct addition of water at low temperature and high pressure. So that's also one way. So here, the reaction that I showed you here H2SO4 is used as a just a what you can say, a catalyst. So basically you end up forming hydrogen sulfate and then water. So that's one way that you can definitely use this as. Okay, now the third reaction that I would like you guys to really know is dehydration of alcohols. So you have this reaction, sorry, you have alcohol here. So there is a hydrogen and there is an OH here and there is another compound here. You use concentrated H2SO4. Please note, in the last case we had used dilute H2SO4 on alkenes. Here we are using a concentrated H2SO4. Listen, H2SO4 is a highly hygroscopic substance. What do you mean by hygroscopic? It is in extreme thirst of water all the time. In dilute H2SO4, incidentally, since it is dilute, it has a lot of water around it. But in concentrated H2SO4, there is only H2SO4 and it needs water, and therefore it will get water extracted from wherever possible. Therefore, sometimes there are also small sachets with concentrated H2SO4 crystals that are used to absorb water from substances where we don't want any moisture. So concentrated H2SO4 is something that we really use here to end up getting an alkene. So the water here gets out and the electrons from here get here to get a double bond. So an alkene is formed with concentrated H2SO4. That is one of the most important reactions. The fourth reaction that you guys should be very aware about is the all the oxidation reactions. Please note the oxidation reactions. Here you use KMNO4, alkaline KMNO4. Then you use acidic K2Cr2O7, or you can also use H2Cr2O7. All of those, are okay. Whenever you use this kind of a reaction, I'm only doing some specific reactions in the interest of time. I'm not looking at all the reactions. These are the reactions that you should not miss out on. Other reactions you can revise as you get time. But these reactions, if you miss out on, it will be harmful, not just for now, but even for your future studies. So both of these basically end up giving an oxygen. Okay, this oxygen, why it is written in a square bracket, is because it's purely just an oxygen atom and nothing else. So once you have an oxygen atom, the sequence is that any alcohol will firstly go to become an aldehyde or a ketone, and the aldehyde and ketone then further ends up being a carboxylic acid. Okay, I'm going to show you just one example. Let's say we have propanol, which is CH3CHOH CH3. When you have an aldehyde, so since this is a 2-degree alcohol, the bond does break. Okay, the bond does break here. So you end up getting two alcohols. So you'll end up getting CH3 CHO CH double bond O. So this is one aldehyde, and then you end up getting CH3, sorry, CH double bond O. So is it one to CH2 double bond O? So this is formaldehyde and this is ethanol or acetaldehyde, and both of them will further end up giving you carboxylic acid, which is acetic acid, and then you have formic acid. Okay. Now, one very important thing. Please note Because the alcohol was in the second carbon, I had to break the bond. It's not simply that you end up getting a ketone, so a few of you might also think that, sir, can it go through CH3 C double bond O CH3? Yes, no problem, you can write this also. That is absolutely right, absolutely okay. But please note, even if you write this, in the end you'll end up getting these two products only. So the intermediary, you can still write this as one of the products and be satisfied for the moment, but in the end you'll end up getting carboxylic acids only. Okay, I hope everyone is there with me. And yeah, there are a few comments, but I would just again ask you, if there is anything, please try and send out on WhatsApp or here at this point. So I'm just coming to the end of the reactions in organic chemistry. This is one reaction that is very important. The other reactions that are slightly important are Toland's reagent. I'm just going to take names here. The Fehling's solution. Okay, these two are some very commonly used, commonly asked reactions. Then esterification, these reactions are also very commonly used. Esterification is a very easy reaction. You can simply use a carboxylic acid, RCOOH, plus you use alcohol, which is R-OH. Please note, carboxylic acid ends up giving OH. This is one another mistake that everyone does. Carboxylic acid ends up giving OH and not H. Although it's an acid, people think that H is given through here and ROH gives the OH. No, it's the carboxylic acid that gives OH. So you end up getting R C double bond O O R dash. So this is the ester that you get. You can also have etherification reaction, ethers. So instead of this, I'm just going to show you a comparison what happens when two alcohols are used. So etherification, in etherification, you basically have R OH plus H O R dash. In this scenario, you have one of them giving out OH. Which one gives? Please note, the one that is smaller, the smaller one will give out OH. So I'm writing here explicitly the smaller carbon group. So you will say, sir, what happens between if these carbon groups are same, different? What will happen? The one that is smaller will give out OH. The one that is larger will retain the oxygen, and it will end up giving ROR dash. So this oxygen comes from the larger one. So this is the larger alkyl chain. I hope everyone is there with me, and you're connecting. With this, I think most of the major reactions are done. There are a few reactions. Oh yes, one more that I recall, which is also important, is the reduction reactions. In reduction reactions, you can use LiAlH4, LiAlH4, okay, or you can use H2 in presence of platinum and palladium as. 1 second, guys. There is a background noise. Okay. You can use hydrogen in presence of platinum and palladium as the catalyst. Both of these do the same thing. They will take alcohols to alkanes. Okay, simply reuse them. They will take alkenes to alkanes. Okay, they will also take carboxylic acids, for example, because carboxylic acids are on a lot on the acidic side, on the oxidation side, oxidized substance. They'll bring carboxylic acids to alcohols, so they can do that. And further, they can also be taken to alkanes, okay, depending on what reagent you're using. If you're using H2PTPD, it's possible to do this, and it's possible till year. Mostly alkanes will not happen. For alkanes, you'll need much higher reduction to be done. Okay, so that's a quick recap on organic chemistry. I think this should be suffice for you to do okay. If you are really looking forward to score very well, I think you should go back to your text and look at the topics one more time. Others, now I'm going to go to the next topic of revision. Can you tell me anything that you specifically want me to do? I am going to take up thermodynamics, but is there anything else that you want me to look at? I'm gonna pause here for a second just to check the comments if there are any. Okay. So till you put up, I'll give. I will just be here for the next topic, and that will do as thermodynamics. Okay. Anything else that people want to really look at? Okay, so I think I'll begin with thermodynamics. Uh, there's nothing specific that probably you have in mind, so I can actually go through the general aspects of thermodynamics. So I'll give you an overview about thermodynamics. In thermodynamics, the topic firstly starts with understanding all the processes and parts of it. For example, understand what is a system, understand what is a surrounding. System is what we study, anything outside of that is a surrounding. Boundary is something that differentiates them. Then there were three types of systems. One is a open system, second is a closed system, and the third one is a isolated system. So there were three types of systems that we had studied. Then the processes that we studied, for example, there were irreversible, then there were reversible processes, then we had isothermal processes, uh, we had isovoluminous, or which we also call as isochronic process, isobaric process. Okay, so we basically looked at an average of all what all the different types of processes that were there. This is just the basic setting of the chapter. Okay, okay, yeah, just to make sure that you guys are all there, I because I don't have a direct connect. Can you please again just put in your confirmations that you are still here? Sachi, Ronak, Aditya, Aishwarya, Arpita, Tripin, Kirtana, Mansi, Ananya, Shomik. Yeah, sorry, I know I'm asking you again, but just put up a yes, no, I'm here, whatever you feel good, like a quick check on whether you guys are still there. Because I want this to be really connecting to you rather than just okay. That's good, Aishwarya. Okay, Ronak is there. Where are others? Hmm. Mansi is there. Arpita is there. Tripan is there. Perfect. Okay. Good. Yeah. Thanks. Thanks, guys. I think the rest are around. Okay. That makes sense. Perfect. So this is the basic setting of thermodynamics chapter. This chapter then revolves on two parts. One, understanding what energies, different forms of energies are, which we also called as different forms of enthalpy. Enthalpy and energy are nothing but just kind of synonyms, words equivalent to each other, said in different contexts, nothing else. And then we said, okay, what is the law of thermodynamics? Okay, what is the law of thermodynamics, which is the first law that we have studied. Okay, now in the enthalpies of thermodynamics, all that you have studied is the following points. The first that you have studied is what are bond enthalpies. Then you have studied what are neutralization enthalpies. Okay, then you have also studied what is ionization enthalpy. Okay, ionization enthalpy. Then you have also studied what is uh, phase change enthalpy, phase change enthalpy. What is formation enthalpy? Okay, formation enthalpy. So there are multiple enthalpies that you have studied. Okay, please note the most important point in all of these definitions. These words themselves say a lot to you. Okay, so if someone asks you what is neutralization enthalpy, you will simply say anything, any energy that is released during neutralization. And what do you mean by neutralization? Simply means that water formation from acids and bases, or salt formation, salt and water that is formed from acids and bases. Someone says what is phase change enthalpy or state change enthalpy? Sir, whenever anything goes from solid to liquid or liquid to gas, whatever energy is released or absorbed is phase change enthalpy. All that is good. The problem happens in these two things, and please note this very well. The first thing that problem happens is mentioning of 1 mole, how much quantity, because energy will be variant with the quantity, right? You tomorrow start the reaction with 10 kgs of the substance, the energy released and absorbed will be different than what you do with 1 gram, right? So most of these are for 1 mole, so it is not even weight, it is for 1 mole of a substance. The second thing is, always try and think as to what is the starting and ending point of the reaction. What is a starting and ending point of the reaction? I'm going to give you an example: starting and ending point. These are the two major things that you should really look at. For example, the starting point is, in neutralization, starting point is, sir, acids and bases. Okay, good. Ending point is 1 mole of water formed. 1 mole of water formed, not 1 mole of salt, or 1 mole of acid and base reaction, or 1 mole of acid, 1 mole of base. No, whatever the acid and base do, I don't care. After they have reacted, 1 mole of water, the moment it is formed, whatever energy has timed out or has been given out, I will calculate that. Phase change, what is the starting point, the initial phase and the final phase? Formation enthalpy. What is the starting point? Elements. Elements is the starting point in formation enthalpy. So you start from elements and you end up at compounds. So that is formation enthalpy. Now, elements themselves cannot come from anything. That is why they are called as elements. So therefore, their formation enthalpies is always zero. Now, elements start from this end and they end at being compounds. So that's formation enthalpy. Now, there are in some of these definitions some additional conditions. For example, in formation enthalpy, the additional condition is that the reaction should happen with natural state of elements. A natural state of compound should be formed. Second, mostly it should happen at STP, standard temperature pressure. Standard temperature pressure is 0 degree Celsius, that is 273 degree Kelvin, and 1 atmospheric pressure. 1 atmosphere pressure. Okay, this is standard pressure temperature. So this is one very important thing that you should remember. Okay, so all of these enthalpies are there: bond enthalpy, neutralization, ionization, phase change, formation. Now, whenever you are in a doubt, so this is the overview. Now, where is the problem that happens, or where is it that you guys really feel very hurt whenever there are signs that come up? Okay, so first I told you about definitions where you should be careful. The first thing is that you should be careful about amount. Second thing, you should be careful about starting and ending point. Third thing, you should be careful about some special conditions. Special conditions, for example, STP or elements in their standard form. These are some special conditions for some of these enthalpies whenever we define them. Okay, so now that's one. The next thing that you guys really go wrong, mostly that you guys find a difficulty, is with the signs. The signs. Now, forget any and all definitions in that scenario. Always think logically. Whenever a bond is formed, C bond, C single bond O, okay, it is obvious that the bond was formed because they wanted to stabilize. Else, why would they stabilize? Or why would they go to form a bond? Since they stabilized, implies energy must have been given out. So I'm going to tell you the basic rule, basic law. Remember this, and all of your equations mostly will be taken care of. Firstly, every reaction is happening for stability. Every reaction is happening for stability. The second point is the stability means low energy. Whose low energy? Low energy of the substances formed. Substances formed. Okay. Okay. That is why any reaction or something, any process is happening. Now, if the substance for some reason is not going to low energy, then you will have to give energy to sustain it. Okay, so this is the third point. Give energy to sustain. Sustain means maintain that position. Why? Because that guy was not willing to. You somehow pushed him up. So obviously that guy is wanting to have you give him energy to sustain his position or state. Okay, sustain his position or state. Right. So these are the three rules that are always applicable. So bond energies, obviously, since energy is given out, bond enthalpies will be negative. Formation energies, obviously the compound is getting formed, therefore compound ideally should be negative. But let's say somehow you have given energy and made that compound form, some orbit compound like ClO2. Okay, now this compound would never want to be there. You have somehow made it formed. In those scenarios, your formation enthalpy will be positive because you have given them high energy to make them sustain there. Okay, then there are allotropic energies, which means change from one allotrop to the other. So all of those enthalpies are the based on the signs are decided from some common sense. Now, change in enthalpy, change, any change is always defined as final minus initial. So change in enthalpy will be final enthalpy minus initial enthalpy, final minus initial position. So check at initial what was the energy of the substances, check at final what was the energy of the substances, simply subtract final minus initial and you will be done. Okay, so I'm going to, for example, so one thing that I want to do, but I might not get enough bandwidth to do it now, is that you guys should be able to solve some problems. There are a few students who are in touch with me, and they keep on sending the problems, multiple of them. In fact, I would suggest that all of you actually do that. I have enough problem. If you feel that you do not have sufficient problems to solve, ping me, and I will send you thermodynamics problems. I will send you chemical equilibrium problems. This is again for those who are willing to get marks. If you're not willing in the first place, then me pushing you is not going to help much. So we have a very free system here. You can enjoy the class and retain whatever information you can, but if you want to score better, ping me and I will send you and I'll help you with the papers. Okay, so with additional sums. So that's enthalpies. Now, one more thing that you have to learn in thermodynamics is Hess's law. Okay, Hess's law. Now, please note, Hess's law is nothing but accounting. For example, something happened, A plus B happened and it gave C. Some other B plus D happened and it gave E. But you were asked to actually talk about A plus 2B plus D, okay, giving C plus E. So you will simply say, boss, when A plus B gave C, what was your cost? Did you take money from me or you gave money from me? In terms, instead of money, here you're asking energy. So you will say, okay, this was H1. H1 was given. And then B plus D, what happened, boss? So you will say it is H2, which was taken. So therefore, this is, since this was given, it was minus H1. Since the second thing was taken, it is plus H2. So you would essentially simply say is that at guys, the total energy here would be H2 minus H1. Okay. So there is a request here, sir. Can you solve an exemplary problem from thermodynamics? Okay, let's do a problem as well. So I'm not going to do a problem from your text, but I'm going to give you a problem that I already have. So, uh, uh, okay, let me just quickly give you a problem. Let me see how I can actually show you the problem. Uh, yes. So let's say that I'm going to read out the problem, and I'm also going to do, I'm going to write the basic important points here. You guys can check. What you guys can do after I've written the problem is write the answer in the comments. Okay. So here's the first question for you guys. Okay. Okay. So so the heat of combustion, here's the question. The question is the heat of combustion. So therefore, delta H combustion is given to us. Delta H combustion means something was burned of ethylene. Ethylene. They have not given uh, the formula. They're given the name. So you guys are okay to use the formula at 18 degrees Celsius. At 18 degrees Celsius and at constant volume. Please note it is constant volume. Okay, at constant volume is minus 355.8 minus 355.8 kilocalorie kilocalorie when water is obtained in liquid state, and here water is obtained in H2O is obtained as liquid state. Okay, calculate the heat of combustion at constant pressure. They are asking calculate the same heat of combustion at constant pressure. Okay, at constant pressure when P is equal to constant. Okay, slightly tricky and not so easy a problem, but doable. So they have said heat of combustion at constant volume is 335.8 kilocalorie per mole. It should be per mole. Now they have asked that the calculate the same heat of combustion at constant pressure. I'm going to give you a minute and then I'm going to start discussing the same. So hopefully you guys get it. Yes. So, okay. So I will I think now that you guys have got a heads up and you might be thinking about it, I'm going to do this one problem directly for you. You can always pause the video if you don't want to listen to the solution, solve it, attempt in 10, then come back. You can always do that as well. But right now I'll just do for again in the interest of time, I'm just going to share the solution with you. So basically we have been given delta HC, which is combustion at constant volume. We know that delta H is equal to delta E plus P delta V. Okay, plus P delta V. Okay. Now at constant volume, the P delta V will be zero because the change in volume itself is zero because volume is constant, and therefore delta HV is equal to delta E, and therefore delta E is equal to minus 335.8. Now we know that PV is equal. This is the solution part, so I'm going to mark a separator between them, aligning between them here also. We know that PV equal to nRT. So therefore, P delta V is equal to delta nRT. The reason is the temperature is again maintained constant. So the only thing that will change if pressure and temperature, they've asked us when pressure is constant, and they have already said that the temperature is constant. So when pressure is constant, then temperature is constant. The only thing that can change is for volume is the delta n part. Now, since we cannot directly find now, Now, see, what we have got is this as part one. Okay. Now we have been asked as delta HP. Now, delta HP is delta E plus P delta V, where pressure is constant. Delta V, E, we already know from this part, so it is minus 335.8. P delta V, since I cannot, there is no pressure given to us, neither change in volume is given to us. So I figure out that P delta V is equal to delta nRT, and delta N is nothing but N products minus N reactants. Now, N products, number of products for this equation, we will figure out is that, let us write the equation. So it's ethylene. So ethylene means CH triple double bond CH2, CH2 double bond CH2 plus O2, since it is combustion, plus O2 gives CO2 plus H2O. CO2 plus H2O. Now here we have asked this for liquid. Okay, this is for liquid. So therefore this will not be considered in delta N, because delta N is only considered for gases. This is a very important point. A lot of people make mistake in that. CO2 definitely is in gases. Now firstly I will balance this equation. This is 2 CO2, and water there are 2 and 2 4, therefore 4 O2, 4 H2O. Now the oxygen that has been utilized are 2 to the 4 plus here 4, so that is 4 plus 4 8, and therefore there is 4 here. Now therefore total number of products is only CO2. Please note H2O will not come into the scenario. Why? Because H2O is in liquid form. This is only gaseous equation. This equation is applicable only for gases, and therefore I will have to neglect the 4 of H2O. So the total number of products here is only 2, that is NP. Okay. Now the total number of reactants is 1 plus wait, oh, this should be 3. Sorry, this should be 3. This, why this is 3? Because 2 or 2 4 here, and 4 here. uh 1 second, 2 CO2. Oh, this should not be 4, this should be 2 here. Yeah, I think, thanks for pointing out, guys. Yeah, so this should be 2 here. So therefore this oxygen will be 3. So this is 2 to the 4 hydrogens, 4 hydrogens match, 2 carbons matched, oxygen 6 here, 6 here, match. So this is the total number of products is 2, total number of reactants ends up to be being 4. Therefore delta N is minus 2. And since delta N is minus 2, my here P delta V will be minus 2. This is minus plus minus 2 into this delta nRT. Instead of P delta V, I'm writing as delta nRT, and that will be minus 2 into R. R will be, since it is kilocalories, therefore it will be 2 into 10 to the power minus 3 kilocalories. And then I will write the temperature. The temperature is 18 degrees Celsius, that is 291 Kelvin. Okay, and so therefore if you really solve this, this will come out to be minus 335.8. This should be somewhere around 2 to the 4, 4 into 300 is somewhere around 600, minus 3 and plus 3 will get cancelled out. So this will approximately come out to be about, uh, so that is 4 2s are 8, so somewhere around 10. I think it should be 10 or 1.9. I think approximately about 1.9. So this should be or equal to about minus 336.964 kilocalories. Okay, so that's the solution for one quick problem. Let's do a problem on Hess's law. That's something that I'm expecting that will be there in your exam as well. So we'll do a quick question on Hess's law. So okay, so here's a question on Hess's law. So it says, before that, a quick revision on the thermodynamic laws, because we have seen this problem, but this problem was based on thermodynamic laws. All we saw in the previous example was Hess's law and the different forms of energies. And then the law basically says that law of thermodynamics is nothing but law of thermodynamics is nothing but conservation of energy. Conservation of energy. Now, what does this conservation of energy mean? Everyone knows conservation of energy, but what is so difficult here? So see, basically, if you have a container and you have a piston on the container, and this container has a gas, liquid, or any kind of substance, if I heat this container, Q is the heat that I give. Okay. If I give anything heat, the energy of the internal substance will increase. The energy is called as U. It is called as internal energy. And when the energy of the internal substance increases, it has the control to push this piston up. If it pushes the piston up, it will do some work. So what is conservation of energy? Conservation of energy said, what did you give? What did you give? I said I gave heat Q. Okay, they said that's fine. So you write this as Q. Then they say, okay, because of the Q, what happened to the energy of the gas? I say it might have changed. So let's write it changed from Ui to Uf. So Uf minus Ui is the change in internal energy. So I write as delta U. Okay, but did all the Q go to the internal energy? No, it did some work. Okay, the work was done by the gas. So yes, I can write this as plus P delta V, the work done. But since we know that in chemistry we write work as done by the gas as negative, we don't want any work to be taken out. So we write this Q as delta U. So this work has to be negative, but here I have a plus sign. Therefore, I write this as minus W. So W is basically nothing but minus P delta V. Okay. So with this equation, I simply get first law of thermodynamics, which is Q equal to delta U minus W. Now, if few of guys, yesterday had a issue as to, sir, what is QV? QV means the heat given at constant volume. If volume is constant, will I have a W? No. So QV is simply equal to delta U. Whatever heat you gave to the system, it simply changed the internal energy of the system. It cannot do any work. So QV is equal to delta U. What is QP, sir? QP, if any heat that we give, if it is changing only internal energy, it implies that its volume will be constant. But let's say if the volume is not constant, if the pressure is constant and the guys are able to push the piston, then QP will be equal to, okay, internal energy will also change and work will also happen. So QP is equal to delta U minus W. Now, a lot of people also have questions on saying, sir, sometimes Q is equal to delta U plus W, sometimes it is delta U minus W. I will tell you, forget about all of these equations. You will never go wrong if you are doing by the fundamentals. And what is the fundamental? Anything that is done on the system is good and therefore positive. Anything that is done by the system is bad and therefore negative. So therefore, what you guys have to really look out as whenever you're writing the equation, forget about the equations and signs and all of that. Do your calculations well. Account for your energies pretty well. If something is getting into the system, call it as positive. If something is coming out of the system, call it as negative. In the end, whatever you gave in should come out. That is conservation of energy, as simple as that. So, don't get trapped into the terminologies and words and signs and all of that. Although it is good to know them, if you, in the worst case scenario, a smart guy would not really be concerned about it. He would simply be concerned about his accounting of the energy. If his accounting of the energy is good, the rest will be taken care of. Okay, so I think you guys are also with me now. What I'm going to do, so this is the one that we have already done. So the revision of the technical things of thermodynamics is complete. There is nothing more in thermodynamics apart from this. So how do we calculate bond energies, allotropic, and all of these enthalpies? I've already told you like a major overview of everything. Now let's go back to knowing doing a problem. Okay, so here's a problem. So the question says that use the following data, and so it says use this data, use the data at all values are in kilocalorie per mole at 25 degrees Celsius, that is room temperature. Okay, so all of these values is at this, and we are asked to calculate the bond energy of CC bond, carbon carbon bond, and CH bond. Okay, this has been asked. What is the data given to us? The data given to us is delta H combustion, of ethane is equal to minus 372.0. Delta H combustion of propane is equal to minus 530.0. Delta H uh, conversion of carbon solid to carbon gaseous, okay, is given as 172 kilocalorie per mole. Bond energy of HH bond is given to us. Bond energy of HH bond is given to us, and that is equal to 104. And delta HF of H2O liquid is given to us as minus 68.0. delta H formation, that is okay, and delta H, that not, forget that not, now not simply means that at standard conditions, okay, and delta H naught of CO2 gaseous is given as minus 94 Kelvin. So this is the data given to us, and the combustion energies are given, and the rest energies are given. We have to find the CC and CH bond energy. Please note they have given combustion energies of ethane and propane both. That is for a reason, because between ethane and propane, you have one carbon extra and two hydrogens extra. So you can use that and do this reaction. So I'm again going to pause here for a few seconds for you guys to really recollect. If you want to pause, you can pause. After about 30 seconds, I would be starting the solution. Okay. So now a lot of these are given to you. You can just note down these points, or you can always pause the video and take down these values. Meanwhile, I go ahead a bit. So here's the solution for it. So when we have C3H8, which is our propane, and when this propane is actually heated, basically the delta H formation for propane is something that if we know, then propane is actually made from three carbons, which is in solid state. Please note those carbons has to be in natural form, and four hydrogen, which in the elemental gaseous form. So if we know this delta H, then this is like we will be able to know the carbon-carbon energies and hydrogen-hydrogen energies. Okay, so let's call this as delta H1. Also for ethane, let's call this as from 2C plus 3H2, 2C plus 3H2 giving C2H6. Let's call this as delta H2. Okay. Now, for carbon, let's call the CC carbon energy as X kilocalories and the HS carbon energy as Y kilocalories. Okay. Now, what we are going to do is from the equation 1, we know that since it is three carbons and four hydrogens, uh, no, not HH, sorry, this should be CH. The CH carbon energy, because that's what we need to find. We're going to find that as, uh, you know, as Y. Okay. So from this equation, delta H1 from delta H1 is given as, it should be equal to 2x plus 8y. Why? Because in C3H8, this gives C3H8. So in fact, let me not draw the arrows here. Let me write this as dot, else you guys will again get confused. So I'm saying that for C3H8 and for these guys, okay? Now C3H8 has two CC bonds. It has two CC bonds. So therefore, and the energy is released when carbon-carbon bond is found, energy is released. Therefore, I'm putting a minus sign. Please note, minus sign, because energy is released. And two carbon-carbon bonds are formed, so that will be 2x, and 8 carbon hydrogen bonds are formed, because this is C3, 1 2 3, 1 hydrogen, 2 hydrogen, 3 hydrogen, 4 hydrogen, 5 hydrogen, 6 hydrogen, 7 hydrogen, and 8 hydrogen. So there are 8 hydrogens formed, and therefore this will be, and this energy is released. Therefore 2x plus 8y will be the released energy. This will be the release energy. But while this energy is being released, the carbon is, there is energy that I have to give also, and therefore I will put this as plus. What energy I have to give? I have to convert carbon to carbon gaseous. That is point number one. And I have to convert hydrogen to hydrogen atom plus hydrogen atom. I have to break these two. So I'm making a star here, and both of those stars I'm putting it here, so that you will remember again. Once you understand, you can always rewind and get back to what I'm saying. So now how many carbon I have to convert to carbon gaseous? 3. So I will multiply this by the 3 carbon gaseous form, which is how much? Yeah, so carbon solid to carbon gaseous is 172. So I will multiply this 3 carbon atoms per, because it's per mole. Please note it is per mole. These are 3 moles that are getting to gaseous form. This is 3 into 172 plus. Now this is the energy that I have to give. So everything I'm putting in plus. And then I have to break 4 hydrogen bonds. So I'm going to write this as 4 into 104. This is 4 into 104. That is what I will write. So basically what I end up getting, and similarly, I will write delta H2 as minus xy, because in ethane I have CC1 bond and there are 6 hydrogens. So the energy that will be released is X. Cc we have considered here as X. So delta H2 will be 1x is released because of carbon-carbon bond, plus how many carbon hydrogen bonds are there? 6. So 6y is a release because of carbon hydrogen bonds. And then what is the energy that I'm giving in, that I'm going to put as plus? I have to now convert again these carbons here, these carbons now. These carbons I have to convert. So let me write that with a hash probably now. So here I'm writing hash this carbon, and here again a double hash. So now these carbon and hydrogen I have to convert so that they react to the gaseous form. So this is the solid carbon that goes to the gaseous form. So that will be 2 into 172 plus 3 moles of hydrogen are going to break down. So that is 3 into 104. So these are the two reactions that I've got now. But I also know that they have also given me that the combustion energy of ethane is given as minus 372, and propane and bond energy of hydrogen is given. So this is just the bond energy of hydrogens that we have used here. Now we have also been given as combustion of for the formation energy of HCO2. So carbon really going to CO to CO2. So this is carbon C. Now this goes to plus O2 being going to CO2, and this has been given to us as minus 94 kilocalorie. Okay, and we have also been given as hydrogen because these are formation enthalpies of hydrogen, CO2 and H2O. So hydrogen with half O2 is being given as H2O. So we have been given this also, which we are going to write it as minus 68 kilocalories. Minus 68 kilocalories. Okay, so we get CO2 as minus 94, and we get H2O as minus 68. This is given to us. Okay, this is given to us. Now when we write the equations for C2H6 so please note, these are the formation enthalpies. Delta H1 and delta H2 are the formation enthalpies. Let me use a different color. This is formed from its elements. This is the elemental form, elemental form, elemental form, elemental form. So this H1 are basically HFs. These are formation enthalpies. So whenever I write C2H6 and combust it here, I'm basically writing the formation enthalpies of this and the other guys. So C2H6 plus 7 by 2 O2 gives basically twice of CO2 plus H2O, where it will be thrice of H2O. Now this is given to us as minus 372 kilocalorie. Okay, this is given to us minus 372 kilocalorie. Now we already know that if we really just okay, one second. Yeah, so now we know this CO2 and H2O's energy. These are the formation energies. So this is 2 into minus 94, and this is 3 into plus 3 into minus 68. So this is the energy that is given out to us. So therefore I'm writing this as minus minus. This is the energy that I have to give, and this will be delta H1, that I have to give in. So all this delta H1 is the energy that we have got that I have to give. So therefore I will write it as positive, and this will be O2 will be 0. So delta H1 is simply going to be equal to all of this. Similarly, this is one equation that I'll get, and let me write it with a capital I. Now similarly, I'm going to write the second equation where I have C3H8 plus oxygen giving CO2 plus H2O. Now oxygen, if I have to balance this equation, this has to be 3 CO2, this has to be 4 H2O, and oxygen will be 5. Please note, in all of these scenarios I have kept this as 1 mole. This as 1 mole. Why this is kept as 1 mole? Although this is I have written as 7 by 2, I have not written this as 2 in C2H6 and 7O2, is because this energy is given me per mole, is given to us per mole. So therefore per mole of whom? It is combustion energy of ethane. So therefore it will be per mole of ethane. Therefore I've kept this as 1 mole, and then I've written everything. Similarly, I'm keeping propane as 1 mole, and then I'm doing everything else. Now this energy is nothing but delta H2, because this is the formation enthalpy of this, and it's positive because I have to give this energy to break down these reactants. This energy will be 0, and going further, this energy will be given out to me. So therefore this will be 3 into the CO2's energy, which is minus 94, plus this energy will be 4 into minus 84, sorry, minus 68. right? So we, and let's call this as equation 2. Now from these equation 1 and 2 we will get two x and y equations. So here is a 1x and y equation. So we solve all of this and we get 1x and y equation, and we get second x and y equation dealt with delta h2. Delta h1 will equate to this, and delta h2 will equate to this. I'm just directly going to tell you the answers. If you, when you solve this, you will get x as equal to 82. You can, whenever you find time, you can rewind this video and you can again go through it. X is equal to 82 kilocalories and y is equal to 99 kilocalories. Okay, so that's the answer. So I think this is a perfect and classic, and I think very complex, and all the components of Hess's law is considered here. Please note that the principles, I'm going to revise the principles that we used. We used the enthalpy of formation from their elemental state. So please check, these were solids and we have used enthalpy from solid, whereas H2 has to be gaseous, so this also has to be gaseous, and this has to be again gaseous, so we have kept this. Now, the second equation that we use is, since solid cannot directly react, we have converted them to gaseous. We have broken down H2 into H and H. This we did because this is where the reaction happens. If I simply put a carbon gaseous and a hydrogen besides it, there is no energy exchange. This is where the reaction happens, but this will need energy, and therefore those energies have to be accounted. This energy, once we have got this delta H1 and delta H2, they are nothing but formation energies of propane and ethane. These formation energies we have further used in their combustion reactions. So we have formed C2H6 and then we have combusted it to give CO2 and H2O. CO2 formation energy we have used, H2O formation energy we have used. Their formation energies and these formation energies we have simply subtracted to get this delta H here. And this delta H is already given to us as 372, which we have used in our further calculation. Delta H1 we know in terms of X and Y, and similarly delta H2 we know in terms of X and Y, and we will be able to solve both of them. I recommend that all of you guys actually go through this example once again after this class. Spend like half an hour, 50, probably 15, 20 minutes if required. And please see what all the steps that we have done. Try to attempt it yourself, try to do it yourself, do the calculations, come back. If you're still stuck, you can always ping me one-on-one. I'm again checking if you have any doubts. I recommend that if you have doubts, you please send them now. I've said this n number of times. It's up to you. If you have anything, please let me know. Now, so that's about thermodynamics. I've also given you two problems on thermodynamics. There won't be any problem if you understand what we have done in these two problems. I guarantee you, even the bond enthalpies, formation enthalpy, combustion enthalpy, all of that have been taken care in these two examples. So check out these two examples and see if you understand them. You should be okay with it. Now, after this, I'm going to go to your chemical equilibrium. One another topic that most of you guys are struggling or probably might have a issue on. So in chemical equilibrium, what we will study. So here's, let's understand the overview of chemical equilibrium like we have done for all the other two topics as well. Right. So in chemical equilibrium, okay, one second. Yeah. So what is the overview of the topic? The overview of the topic is, it starts with understanding what is a what is basically a reversible reaction. Okay, so a reversible reaction is when you have forward and backward reactions both happening simultaneously. Then we understand, okay, if there is a reversible reaction, it does not mean that there will be, the reaction will simply keep on changing its concentrations at all point of time. The forward and backward reaction eventually at some point of time come to an agreement where both the concentrations of, let's say, AA plus BB giving CC plus DD, both of these actually come to a standstill. So that is when we say that equilibrium is achieved, which means that the forward reaction and the backward reaction have now got balanced to have balanced each other. This is where we come to say, okay, if there are these rates, then what is the rate about? And this rate is basically defined as amount, change in amount. So delta amount, I would say delta amount. Let me write it again. Delta amount divided by delta time. Okay. So now amount can be written in any, quantity can be written in any way. For example, kg, moles per liter, density, volume, even color, even the texture, size, or all of these can also be used to define rate. But what we basically use here is a common language where you and me both should be able to talk in the same language, and therefore we end up doing the rate of reaction in terms of moles per liter per time. So right, so amount we write in terms of moles per liter, and we take this with change in time. So this is a standard convention in which rate of reaction is written as. Once the rate of reaction is understood, then the next thing comes as to, okay, what does this rate really depend on? And there comes your law of mass action, where law of mass action says the rate of any reaction is basically dependent on the concentration that is proportional to the concentration of the substance. And why it is proportional to the concentration of the substance is because the reaction technically happens in the, one second guys. Yeah, so so why is it proportional to the concentration is because now concentration means how many substances are present per unit volume, and the more the number of substances present per unit volume, the more collisions will happen between this substance and all the other substances. The more collisions happen, the more reaction will proceed, the more there will be a, you know there will be a transformation of these substances to give products and vice versa. So it's a very simple theory. This theory is called as collision theory, just for some people who want to read more, but I know you don't have time to till tomorrow. But at some other point, if you have any discussion, you can simply think of this as a collision theory. Then okay, so this is law of mass action, where we say rate is proportional to the concentration of the solution. So we say rate of forward reaction RF is proportional to A and B both. So therefore it should be A to the power A into B to the power B, where A and B are concentrations of substance A and substance B. Now, since there is a proportionality, if you have to make it an equation, we'll simply put it as constant K. So it is K into A to the power A and B to the power B. Simple as that. Okay, good. So this looks so far so good. Once this is done, now just for your understanding, law of mass action, if you want to really have a definition for it, we can say that at constant temperature, the rate of a chemical reaction is proportional to the product of the molar concentration of reacting species with each other. Okay, and this each term raised to the power equal to the numerical coefficient. So what we call as this is A and B are the numerical coefficients. So each of them raised to the power of numerical coefficient of that species in that chemical equation. Okay, so that's the description of law of mass action. I have said this on the video, so you can again, as I said, always pause and come back and revise it if required. Now, so that's law of mass action. Now, essentially, when the reaction begins, so let's say A plus B is giving C, so A plus B will have a very high concentration. So let's say this is the concentration and this is the time that we are using. So A plus B will have very high concentration, its concentration will drop, and eventually it will become constant. Similarly, so instead of dropping like this, probably actually it will drop in a the curve will be very quite different. So the concentration actually drops like this. Yeah, it will drop like this and it will become constant. The concentration of products, so this is reactants, let me call this as the reactants here. But on the other side, the products will start from 0 and then it will become constant. So let's call this as products. And essentially they become. Please note again, a lot of people who do the mistakes is that they make both of these concentrations same. It is not necessary that the concentrations of products and reactants will be same. Not possible, not necessary, not not a part of any sort of equilibrium. The only thing that actually becomes equal is the rate. So if I have to draw here, I think it will be too much to draw here. So if I have to draw the rate of reaction graph, then if this is the rate and this is time, then the rate of forward reaction would actually decrease and the rate of backward reaction will also increase, and they both will become the same after a certain point of time, where here RF equal to RB. So this is the rate of forward reaction and this is the rate of backward reaction. As the forward reaction decreases, the backward reaction increases, and then they become the same. So this is the first major part of chemical equilibrium. After this RF equal to RB, we write their expressions saying that KF into RF is with A to the power A and B to the power B is equal to KB into C to the power C and D to the power D. And now we write KF by KB because KF and KB both are constant, so this entire division should be a constant, and we call that as KC. and therefore because of this kf by kb, kc turns out to be c to the power c and d to the power d instead of a on the top and b on and c on the bottom. Okay, so this is why the expression comes out to the way that it is on your screen right now. So this is Kc, which is concentration of products divided by concentration of reactants. Now the rules for writing this Kc is they are always written in moles per liter. That's very important. The second thing is it should always be homogeneous. All of these has to be homogeneous. Now please note this rule is nowhere said, but I'm giving it to you just as a thumb rule again. If you have gaseous products, if you have liquid products, if you have solid products, and sorry, I have to put in an aqueous here as well. Uh, gaseous, sol, okay, liquid, then solid and aqueous. Okay, sorry, it will be aqueous and solid here. It would be aqueous and solid. Or no, it was right, I'm sorry, my bad. Okay, so it was solid and aqueous, yeah. So now what does this mean? This means that if you have a gaseous product in the reaction, aa plus bb giving cc plus dd, then if any of the product is gaseous, forget about writing all the other products. You don't need to write all other products. Your k will simply be that product. Now let's say you don't have gaseous, you have liquid and all the other products, then only consider the aqueous product. Okay, only consider the aqueous product. So what I'm basically trying to say here is that gaseous product is considered better than okay, so it I'm gonna change this again for you. Gaseous is considered better than aqueous, considered better than liquid, considered better than solid. So unless all products are in solid, you never write any of all of these, any solid product. So if you have gaseous products, write all gaseous products and forget about any all the other products. If you have aqueous products, write all aqueous products and forget about liquid and solid products. If you have a liquid product, write all liquid and forget about any solid product. So always take these side, always consider this side as priority or preference, is what I'm saying here. I'll give you an example. Say a b b c c and d d. Here you have one product which is aqueous and all the other products are liquid and liquid. Okay, all three are liquid and this is aqueous. Your kc will nothing but be simply d to the power d, only aqueous. You don't even have to write any other liquids in the reaction. Similarly, if you have even one gaseous product, you only write the gaseous product. Now please understand why are we doing this. We're doing this because if you have a solid product, its concentration barely changes. It's so small because it is not occupying any volume. It is so concentrated, so its concentration does not change. So what is the point in keeping it in this expression? Because here it will simply remain a huge number without any variation. To give you an example, this can, let's say a will be 10,000 and b will be zero point 0.1. So this 10,000 will simply be lying here, and any change in 0.1 going to 0.11 or 0.09 will not make much of a difference to 10,000. But it will make a huge difference if we take 10,000 to the Kc side and make it as 1, and then we change 0.1 to 0.99 and all of that, then the numbers will change very rapidly of K. So that is one important aspect. So anything that has a huge concentration with respect to anything else, that we will consider as constant. Okay, so that's the simple rule or logic that we are going to use here. This is for heterogeneous products. For homogeneous, you don't have to worry, you can take everything. Okay, homogeneous means all are liquid, all are solid, all are aqueous, or all are gaseous. Okay, so that's one. Now the second thing that we had studied was Kp, where in Kp we said we will write it in terms of pressures. This is pressure of A to the power A, pressure of B to the power B, pressure of C to the power C, and pressure of D to the power D. So these are all partial pressures, and the earlier one were concentrations. I'm just going to give you one more quick good rule is P, since PV equal to nRT, and we are talking about gaseous substances, homogeneous gaseous substances. We know that P is equal to N by V RT, but this is nothing but moles per liter. This is nothing but moles per liter, and therefore this is nothing but concentration of a substance C into R and T. Concentration of a substance C into R and T. Okay, so since it is the concentration, I can always write pressure in terms of concentrations and RT. So if I write these pressures in terms of concentrations, this will be simply A to the power A, RT to the power A, into b to the power concentration of b to the power b into RT to the power b and divided by c to the power c into RT to the power c and d to the power d into RT to the power d. Now guys, please note here I have taken c downwards and a upwards. Does not mean that, so this is always products. I have just taken a general case. You guys will again get confused, sir. In the last question you took c upwards and now you're taking a upwards. No, I'm clearly mentioning it here on the video also, is that the upper numerator has always to be the products and lower denominator has always to be the reactant. So in this case is our where cc plus dd is actually giving us aa plus bb. So we have changed the chemical reaction. I'm just showing an expression. So now I have written all of these pressures. I have written in terms of concentrations. Now, therefore, I end up getting Kp is equal to a to the power a into b to the power b upon c to the power c into d to the power d into RT to the power a plus b minus c plus d. Okay, now this is equal to nothing but Kc, and a plus b minus c plus d is basically delta n, because this is RT to the power np, n products minus n reactants. This can also be sometimes we call as delta n. So this is delta n, which is this. So this is a relationship between Kp and Kc, and that also sometimes is good and useful for you to have. So that is the second concept in chemical equilibrium. The third and most important concept, the last concept of this is no, there are two, one more concept. Yeah, the last concept. This is now about reaction quotient. So we are saying that look, at equilibrium, all the concentrations are fixed. So at equilibrium, Kc is equal to have a fixed concentration of Cc, Dd, and Aa and Bb. Okay, but I am saying that okay, if that is the concentration, then mm, okay, this is the concentration. Then what happens if I change the concentration of, let's say the reaction has not reached equilibrium? How do I know that when will it reach equilibrium? Where is it going? What is happening to it, etc.? So what I do is I simply take a ratio and call it as Q. This ratio may not be at equilibrium. This is not at equilibrium necessarily. This is not at equilibrium necessarily. It might or might not be. So therefore, it is not at equilibrium necessarily. Uh, okay, necessarily. Okay, I've done some mistake here or whatever. Okay, not an equilibrium necessarily. So I simply say that Q is equal to this ratio, simple ratio as c to the power c, d to the power d, and a to the power a, and b to the power b. Let's say I end up getting Q to be greater than the K value, which is given to me. It implies that my numerator is greater and my denominator is lesser. Therefore, the reaction will bring down the numerator and increase the denominator, which means that this will go from products to, this is the products, right? This is products to reactants, and therefore the reaction will go backwards. So Q is greater than the implies that the reactions will go backwards. If Q is less than K, implies that my products is lesser than my reactants, and therefore the reaction will go forward. And if Q is equal to K, implies that the reaction is already at equilibrium and there will be no change. No change. So this is one reaction quotient problem that will come to you, where you might be asked for multiple times as to what are the different ways of really doing, what are the ways of the progress of the reaction based on the QC and K values. Okay. Now the last topic which is important, there is one topic where we have different factors that will actually affect the chemical reaction, but more than that, the most important factor is Le Chatelier's principle. There is only one T. Yeah, so Le Chatelier's principle, or Le Chatelier's principle, simply say that anything that you do to the reaction. Now, when you say that you are doing to the reaction, means you are doing to the surroundings. For example, you increase the pressure of the surrounding, you increase the temperature of the surrounding, you put some substance in the surrounding. Now, this surrounding will start affecting the reaction. Now, the reaction earlier was in an equilibrium with the surrounding. You came in and you did some disturbance. You added pressure, or you added some extra substance, or you simply put in heat. Whatever you did, the reaction will now try to achieve another equilibrium with the surrounding. I'm going to tell you a story about it. It's like saying you were living very peacefully in the community, in the society, in the building that was happening. Suddenly someone came and started parking in your parking slot. Obviously your routine is disturbed and you're angry about it. So what do? Then you go to the society and you say, okay, look, this is my parking spot. The society guy says, look, they don't have a parking and there is a problem with the society. Let's sort it out. So what do? Then you wait for the society to sort it out. Then you both come to an agreement. If there is no other space, then you will say, look, keep it for some days, but after some days allow me also to park. If there is a solution, you will say, okay, take that space there or put it outside or whatever it is. So you will come to an agreement and understanding with the society over a few days. That is exactly what is happening here. The reaction was in equilibrium with its surrounding. Someone came and increased its temperature, put in some substance, increased its pressure or whatever it is. The reaction now wants to have the equilibrium again. So what does the reaction do? The reaction nullifies or the reaction reverses whatever you did to the system. Okay. So for example, you increase the temperature of the surrounding, the reaction will behave in such a way that it will absorb heat. So you increase the temperature, the reaction will absorb the heat so that the temperature of the surrounding comes down. You increase the pressure, the reaction will actually start compressing itself. The reaction will work in such a fashion that it will compress itself so that the external pressure is brought down, and this increase in pressure is again brought down to the normal value. Sometimes it so happens that the entire pressure cannot be consumed, so you will come to some equilibrium point, which is okay, right? So let's say you increase the pressure by 10, so reaction will not be able to accommodate all the 10 atmospheres. It will accommodate 5 and it will keep 5 in the surrounding and will say, okay, now it is an agreement between you and me that the 5 pressure be maintained. This agreement is decided by the k value. So whenever any change has happened, you basically try and find the q. After the q, you again change the, wait till the q goes to k, because the q will tell you whether reaction is going forward or backward, and it will again go to either a reaction going forward or going backwards, depending on what is the case. Now what I'm going to do is I'm just going to quickly do a problem for you, and then maybe you'll have an understanding of it in a much deeper deeper manner. Okay, so let me give you a problem on chemical equilibrium. A quick question: is everyone there with me? Okay, I think everyone is there. Yeah, people, you have questions, please post. Don't feel free. If you don't want to put it on the comment, you can always text me personally. My WhatsApp is just besides me, so feel free absolutely to be uh, uh, you know uh, on the group, etc. Or not on the group. Even if you want to give it to me, send out personally, that's also okay. So okay, so I see that I don't have any other questions or queries or problems. Okay. Okay, fine. So then I'll proceed towards the problem. So, so here's a question. Okay, it says that for an exothermic formation of sulfur trioxide. So here's the question. So the question says that twice of SO2 plus O3, both are gaseous in form, gaseous in form. Uh, okay, and it is giving out twice of SO3 gaseous. Okay. uh, Essentially they are saying is that Kp, since they see, note, all of them are gaseous, so therefore I have no other choice but to use Kp, because that is the most uh, comfortable and convenient formula to use. So 40.5 per atmosphere, and this Kp for this reaction is given at 900 Kelvin, and delta H of the reaction is given to us. Delta H of the reaction is given, and this delta H of the reaction is equal to minus 198 kilojoule per mole. Okay, this is the data given to us. The first thing that they have asked us is write the equilibrium constant expression for equilibrium constant Kp for this reaction. Okay, so Kp is question mark they have asked. Then the second thing that they have asked us is at room temperature, that is at 300 Kelvin, approximately at 300 Kelvin, what will be Kp? Will Kp be larger? They have asked Kp will be larger, or will it be smaller, or will it remain same? Okay. or equal to Kp at 900 Kelvin. Okay, so they have asked this as the second question. The third question that they have asked is, how will the equilibrium be affected if the volume of the vessel containing the three gases is reduced? So volume is reduced keeping the temperature constant. Volume is reduced with T equal to constant. What happens? Okay, so they have asked what happens with that. And the fourth question that they have asked is, what is the effect of adding 1 mole? So we are adding plus. So we are adding plus 1 mole of helium gas, He gas. Why we are adding helium? Because helium is unreactive to a flask which contains SO2, O2, and SO3 at equilibrium, to a flask which contains above reaction at equilibrium. Okay, so this is what they have asked. Now, again, I'll pause here for 30 seconds so that you get time to pause this whenever you are listening once again, after this session, and you can. Meanwhile, if you have questions, you can post them. I'm just looking at if you have any other questions. Okay, so there are 13 of you here. A lot of you are not there. I don't see the Adityas and Anirudh and all of the other people. Even Tanisha is not here. Uh, Ravi Kiran. Okay, then Momika is not there. Ruhi is not there. Dhatri is not there. All of them are. I don't know where these guys are. Hopefully, they watch this video once again and probably get enough of the understanding for tomorrow's exam. Maybe that helps them. Okay, coming back. So you could pause here, and now I'm going to give you the solution in just in case if you uh, again wants to recheck. So check now from the equations that it is firstly an exothermic reaction. So that is very important to know. The second thing is this is at a very high temperature, exothermic reaction at a very high temperature. Kp is 40.5. Okay. Now, so first thing that they have asked is what is the expression for Kp? So Kp expression will be nothing but partial pressure of SO3, that to the squared. It will be squared. Why? Because it is 2SO3 divided by partial pressure of O3 plus partial pressure of SO2 square, into, sorry, this is not plus, this is into partial pressure of SO3 square. Now there was a one very funny question that I had. Okay, is that someone actually questioned me saying that, sir, the delta H of formation of elements we take as 0, so why are we taking that in partial pressure here of elements? Now, please understand, these are completely unrelated topics. The delta H formation is enthalpies and energies of the elements. This is chemical equilibrium, that is thermodynamics, where we are talking about energies. Here we are talking about rate constants. In rate constants, elements will be taken care of. They have to be put here into the rate expressions. Okay, so please don't relate something from some place to something else completely unrelated. Okay, so this is Kp, where we have this is the expression Kp for that. The first question is solved. Then the second question, at 300 Kelvin, Kp will be larger, smaller, or equal to Kp. Now please note, at 300 Kelvin, we have decreased the temperature. This is an exothermic reaction. Since we have decreased the temperature, the reaction will run forward. This will run forward like anything. Why it will run forward? Because it wants to give out heat to compensate the decrease in temperature. So it will want to give out a lot of heat. Okay, so since it wants to give out heat, SO3's pressure will increase, and SO2 and O2's pressure will decrease because the reaction is going forward, and therefore Kp here will be larger. So the answer here is very, very large. In fact, it will be very large than what it was at 900 Kelvin. So at 300 Kelvin, Kp will be much larger than at 900 Kelvin. So that is the second scenario. Okay, I'll repeat again, because this is an exothermic reaction, and we are decreasing the temperature. So decreasing the temperature favors exothermic reaction, because the reaction will want to give out more heat at a lower temperature to balance out the change in the effect. The third thing is what happens if the volume is decreased. Now please note, the volume of the products is 2 moles. Okay, 2 moles. 2 moles is at products, and the total volume here is 3 moles. Okay, 3 moles at reactants. So if reactants are more, then volume is more. If products are more, then volume is less. Now we are decreasing the volume, means the reaction will want to increase the volume. So the reaction will go from products to reactants. So if volume is decreased, the reaction will go backward. The answer here is backward. Okay, so the reaction will heavily start moving in the opposite direction. And what will happen is that the SO2 and O3's volumes will increase a lot than SO3's volume. SO3's volume will diminish. So the proportion of SO2 and O2 in the reaction mix will be more. The last question that they're asking, what happens if 1 mole of He gas is added? Now, please note, 1 mole of addition of He gas is doing nothing but except for increasing the pressure. So this has nothing to do with the reaction. It is simply going to, because one more substance has added into the solution, the total pressure of the system will increase. Why? Because in the same volume, now 1 more mole of hydrogen has helium gas has to be added. So the total pressure has now increased. Now please check. Here there is 2 moles, so therefore there is lesser pressure. Here there is 3 moles, therefore there is more pressure. And we have increased the pressure. Since we have increased the pressure, the more pressure will go to lesser pressure to accommodate the increase in the pressure. That is Le Chatelier's principle. So when we increase the total pressure, the reaction will go forward. The reaction will go forward. Okay. So that's the quick answer to the question. So all the four answers have been given to you, and I think that brings us to the last topic in chemical equilibrium. If you have understood today's lecture, I think we have really done about whatever is going to come to your paper tomorrow. 60 to 70% will be from this, whatever we have discussed. Apart from, I mean, in these topics, not from the other topics. Also in these topics, I think now the only remaining part remains is how much you assimilate and really are able to reproduce tomorrow. Okay. So now again I'm going to pause. I think what my agenda was there for today's class, I'm more or less at the end of it. I would like you guys to again question anything if you have. I'll wait for a few seconds if you have anything to talk about. Else I'll try and we will try and connect on something else. As I said, I'm again available on the uh, phone. If you want, please let me know, and I'm here. So I'm just pausing here because I think there's much that we could do, and we could connect. Yeah. Okay. So it seems that yeah. So it seems that all of you are content. Yeah. We are also coming to the end of the time. So can you guys quickly tell me whether you guys were, so instead of just saying we connected and all, please try and share what did you feel? How is the exam? Are you prepared? Not prepared? Can you just put in a few comments and let me know how you guys were? How do you guys feel about tomorrow's exam? Yeah. Are you ready? Do you feel confident? Do you feel okay? Do you feel stressed out? All well? Huh? Yes, I'm looking forward to your connects, to your messages. Okay, so there are, I think, only 5 of you here around now. If there's anything from you five guys, just let me know. Else, we can stop here. Just put up a comment. All those who are watching, if you feel that there's anything that you want to mention, you can just put in here all, or we can pause here. Mansi, Arpita, Ronak, Aishwarya, Tripan, Kirtana, Sachi, Aditya, Shamik. Yeah. If any of you are here, just please let me know. Uh, or else, yes, please. Mhm. Okay, so it seems that all seem to be good. I don't see any responses coming on. It seems that you all are okay and doing good then. So almost done, but still a bit nervous. Okay, good. I think being nervous is also a good healthy sign. Just don't stress yourself. But I am sure that you will do good. I think actually you have been studying as well. So um, I expect you to do well, so don't worry about it. With if you have understood what we have done today and if you feel confident about it, I think you'll do pretty well in the exam. Not an issue. Okay, Tripan, Arpita, Mansi, I think you all will anyways do good. Kirtana also will do good. Aditya, yes, I think you have been connecting. Aditya, if you have any issues, ping me on WhatsApp as you have been doing. I will also try and help there. Ronak, if you have anything, you can always let me know. Okay. So I will not take much of your time. I think you guys have been fantastic already with all the work. All the very best to you. My best wishes. Just feel free to connect. Also, please do send me a message. How did your paper go tomorrow? And I really think that there will be only all the good news that would come in, and not really anything else. So let's pause here for a bit, and you guys are free to study. Use your time well. Okay. All the best. Take care. Bye bye. Thank you. The video will be here on the YouTube in another 5 minutes. You can always refer to that. Yeah. Take care, guys. Bye bye.